we'll get out of the way so that Christopher can talk to you about his subject. Thanks.
Thank you. I've been attending ShmooCon for well over a decade now, and this is the first time I was convinced to submit to the call for papers, so I'm happy to be here to present about fault injection. And just to quickly elaborate on the presentation title, the lowering of a theater curtain signifies the end of an act or performance, and I think you'll find this is really a fitting metaphor. I found it frustrating while researching this topic because resources mostly fall into two categories: tutorials on well-understood targets, or advanced academic papers typically covering specific techniques. So I hope to fill the gap with a case study documenting my process of exploring a new target from start to finish. If you're watching this, I assume you have at least some basic prior experience with microcontrollers. However, I speak from the perspective of a beginner to fault injection, as this was my first complete success using these techniques. And so, this story begins much the same way as many of my hardware reverse engineering adventures: a late night impulse purchase, anticipation as it's slowly transported from a distant country, then the frustrating realization that it doesn't work quite the way that I want it to, subsequent sleepless nights in pursuit of a workaround, and finally, at least in this case, a satisfying conclusion. The device that caught my attention this time is this RF transceiver module. It is a small, castellated, postage stamp style board with an integrated 2-watt power amplifier targeting either VHF or UHF. You can think of it as a walkie-talkie on a chip that you can add to a design for less than the cost of a ticket to the cinema. The product photos, unfortunately, don't reveal a whole lot of detail. The bottom of the module has labeled pads for surface mount application, while the top is completely obscured by a metal shielding can. The 4 unlabeled pads on the bottom are for a programming interface, but I'll explain this later. Now, here's a block diagram illustrating how the manufacturer intends the product to be used. You can see that adding just a few additional components results in a complete and functional radio design that you could use to communicate with other analog, frequency modulated radios. And this is a compelling use case on its own, but I personally find digital radio modes to be a whole lot more interesting. So what will it take to get this module to support other modes like DMR or P25 or the more recent community effort, M17? Without getting into too much detail, these modes all use 4-symbol frequency shift keying modulation, which would likely get destroyed by internal filtering. Now let's take a look at the command set. If you've ever experienced the joy of working with a dial-up modem, this might look a little familiar to you. The module implements a haze-like command set exposed via a serial port. A small number of attention commands provide a mechanism for configuring various parameters. Unfortunately, I had already heard reports that despite having options to disable filtering, it wasn't sufficient. An inconvenient workaround is to open the module and completely bypass the internal microcontroller for direct control. So after removing the shielding can with a hot air rework station, we get our first glimpse at the internals. The upper left section includes the part that exposes the command set over serial port. The chip module, or the chip marking indicates it's a 0C002. There's no vendor marking. So great, I've never heard of one of these before. The entire right side of the module corresponds to the integrated power amplifier and supporting circuitry. And in the bottom left, there's the actual RF transceiver component. And this is the chip used at the heart of many radios, including the notorious Pofeng UV5R. It's also used in many other radios, including the MD-UV380, the HD1, the GD77, and so on. So it really is a walkie-talkie on a chip. Now, many of the radios that I mentioned are DMR-capable radios supported by OpenRTX. OpenRTX is a custom from-scratch firmware replacement for digital amateur radios, primarily supporting the M17 digital mode. Conveniently, it includes a driver for our transceiver component. And most importantly, the authors discovered that an undocumented register needs to be poked in order for the transceiver to work well for digital modes. If I ever wanted to build something at scale with these modules, removing the shielding can and bypassing the microcontroller sounds really inconvenient. So the next step is figuring out if it's possible to either patch the microcontroller's existing firmware in order to support this setting, or outright replace it with a new one. Through various part inventory websites, I found that this might be the Renesas R5R0C002. If you've never heard of them, you might be surprised to know Renesas is consistently one of the top suppliers of microcontrollers in the world. You would never know this by looking at popular parts used in hobbyist designs. And like many other semiconductor companies, Renesas is really several other semiconductor companies in a trench coat, including NEC and the chip units of Mitsubishi and Hitachi. But unfortunately for me, Renesas doesn't even acknowledge that this part exists, and it seemed impossible to locate the correct data sheet. So I continued digging to try to find more information on this part. And by the way, if anyone knows the name of their strange cartoon fish mascot, I'd really love to know. Forum posts like this one suggest a couple of compatible part numbers that I could use as a starting point, and this is certainly better than nothing. These part numbers are for microcontrollers using the R8C tiny architecture belonging to Group 1B. As far as I can tell, the group designation is an attempt to classify the dizzying number of capacity and peripheral combinations. And thankfully, there are actually data sheets available for these parts. So here's a quick overview of the architecture. The R8C product line was designed to be a cost-reduced subset of its parent M16 family. The internal data bus has been shrunken to 8 bits, and there are 89 instructions with 8 addressing modes. There's also a simple flash programming protocol, and there's support for flash memory protection. So let's look at this protection scheme a little more closely. This is the fixed interrupt vector table, which resides in the last page of the microcontroller's flash memory. The high bytes, however, are partially reserved for an ID code consisting of 7 bytes. In programming mode, the boot ROM uses this ID code as a password to unlock access to the memory flash pages. Keep in mind that this ID code has nothing to do with the interrupts. It's just where the manufacturer decided to store this sequence. And product designers can optionally configure the sequence to protect their firmware from tampering or theft. Since reading, writing, and even erasing the flash memory is impossible without first unlocking the boot ROM with a valid ID code, theoretically. I tried to implement the flash programming protocol, but I couldn't get a response from the chip. So I kept searching, and eventually I did locate the correct data sheet. Apparently this is a further cost-reduced part that was only ever offered to the Asia market segment. And it turns out this specific programming mode that I tried is not supported. Now, once I switched to the mode that's actually supported by the boot ROM, I was able to get a response. Ordinarily, a device with an ID code of all once is automatically unlocked by the boot ROM, and this is a requirement so that blank flash cells in a new factory part can be programmed. That's definitely not the case here according to the status register, so I had to find a way around this. I wasn't looking to reinvent the wheel, so I immediately went looking for any known attacks against this protection scheme. I stumbled across this presentation. It's not specifically about R8C, but knowing that it's a descendant of the M16C architecture, I figured there might be some important lessons to learn. So Serge and Mikwa identified a textbook timing attack against the boot ROM used by an embedded controller in a Toshiba Portage laptop. A pin on the microcontroller is used to indicate boot ROM activity, and it actually leaks information while processing an unlock request. By measuring time deltas, the ID code can actually be guessed byte by byte. Unfortunately, my part has no such pin, but maybe this information could be found through a power analysis side channel. I really wanted to get a better understanding of these techniques anyway. Now, while prototyping my attack, I used the Chip Whisperer Lite. I primarily wanted to take advantage of its Python framework and Jupyter notebooks in order to get up and running quickly. And this is far from the only option, though. You might be better suited using an oscilloscope and a microcontroller dev kit that you already have. For fault injection experiments, don't forget to add a fast-switching N-channel MOSFET. Here's a schematic diagram for my device under test. In order to isolate the microcontroller from other components on the RF transceiver module, I removed it using hot air and placed it onto a breakout board. The 4 pins used are the same ones exposed through the unlabeled pads on the bottom of the module. Now, some of the supporting components in this diagram changed over time, such as removing the capacitors for glitching, but this was a good starting point to see how the behavior was on this module. So using this setup, I was able to collect some power trace data during unlock requests. And ignore the missing axes labels for now, but what stands out most is that with incorrect attempts, regardless of the number of bits or bytes correct, the plot shows 7 evenly spaced segments, corresponding to the number of bytes in the ID code. This suggests that the boot ROM is comparing in constant time and that it's not vulnerable to the same type of attack. Additionally, on a successful comparison, 7 more segments are present. And I kind of speculate that this is a secondary validation, maybe as a mitigation against fault injection attacks, or some other unintentionally successful comparison. Either way, it would be significantly more difficult to successfully land a glitch twice with the correct timing. So during boot ROM execution, this microcontroller is clocked by an internal reference running somewhere around 8 megahertz, and that's further divided by 32 to present a system clock of only 125 kilohertz. While this makes for a slow-moving target, it introduces a whole lot of jitter. You might be able to see the signal shifting side to side between frames of this animation of successive unlock attempts. The Chip Whisper API includes some interesting pre-processing techniques for dealing with jittery traces, but I think in this case my traces are just too far gone. So over the course of several days, I collected hundreds of thousands of power traces of unlock attempts. I tried plotting the data in various ways of hoping to find some indication of ID code, bits or bytes, leaking through power consumption. And here you can see in these two waterfall plots, there's a pretty drastic difference by introducing these pre-processing techniques. There's significant artifacts due to the excessive jitter. I also attempted a correlation power analysis, which is a very interesting and successful side channel attack, primarily for leaking keys from cryptographic implementations. But in this case, the ID code verification is significantly less complicated, and I think there just isn't enough information embedded in the power trace data. Even after enlisting the help of a few friends, it looked like there was really nothing more to be gained on this front. So onward to fault injection. The classic fault injection attacks are clock and crowbar glitching. Both can cause microcontrollers to behave erratically, but crowbar glitching is really the only option of the two for this target. With a crowbar glitch, the microcontroller's power supply is momentarily shorted to ground. And this can cause instructions to be skipped or modified, register contents to change, and this sounds like a good approach for my problem. But the real important question is when. I got very fixated to the idea that I either needed to glitch the actual unlock attempt or otherwise be able to modify the status register reported by the lock state. After several nights, I had nothing to show for my efforts. So I did what any reasonable person would do, and I gave up, at least for a few weeks. Revisiting the problem with a clear mind, I decided to ignore the ID code unlock procedure completely and just directly try glitching against flash page reads. It took some trial and error to find a good parameter range, but I settled on this functional glitching routine. It's important to keep the loop as tight as possible by avoiding any extra commands or resets in order to reduce the time per iteration, since this could require thousands of attempts to get right. However, a successful glitch during a flash page read while locked causes the microcontroller to emit a 256-byte page of data instead of nothing at all. This doesn't necessarily mean a valid ID code, but it's quick to slice it out of the expected offsets and then verify it through an unlock attempt. And so the culmination of this effort leads to this exciting moment, a tool to extract the ID code from a protected flash and dump the full contents. As it runs, glitches are swept over flash page read attempts. Occasionally, various pages of flash are dumped and possible ID codes are extracted and tested. This can take anywhere from a few seconds to a few hours, depending on how lucky you are. Until finally, a successful match. So now we can unlock the boot ROM and do whatever we want to the flash memory. Here I've saved a copy of the contents for analysis. And maybe I can patch it once I get some more sleep. So in the end, I learned that fault injection attacks really aren't just a hoax by big InfoSec to sell more glitches. These are practical attacks that are within reach. I would also like to make a desperate plea that if you find yourself motivated by a piece of hardware, please save all of the relevant data sheets and tools that you can find before they disappear forever. And of course, if I don't miss the publication deadline, be on the lookout for the full write-up and code in the next issue of POC or GTFO. And one last thing, thanks to Travis Goodspeed and a bottle of fuming red nitric acid, we can see what's really inside of this chip. Hopefully you had an opportunity to see his presentation earlier today. So the part number there belongs to components in a completely different group, and this is evidence that the die is shared by multiple parts in the same family. And also check out that date code from 1995. That's a really long legacy for a part that you can buy in a product sold today. And this is the end of the story for now, so thank you.